Hi, everyone. As you may have guessed, this mini lecture is on the Atwood machine. The Atwood machine is a simple machine connecting masses by strings over a pulley system. And it's named after George Atwood, an English mathematician who made one of these around 1784. And it's a simple machine also in the sense that the ratio of output force to applied force is not necessarily one. And we will seek to understand the dynamics of this machine by using some of the laws of motion that you may be familiar with from mechanics. And we will start with Newton's laws of motion. The first one being the law of inertia. An object in motion will stay in motion unless it's acted upon by a force. The next one, Newton's second law, the sum of the forces acting on an object is equal to the mass times the acceleration. And notice this is a vector equation, so direction matters. And Newton's third law, every action has an equal and opposite reaction, or F of A on B is minus F of B on A. And we also have constant acceleration equations of motion, the first of which being the second derivative of position with respect to time, or the acceleration, which is also the first derivative of velocity with respect to time. Again, we're in a constant acceleration situation, so A is constant, and this is in one dimension. So we don't have vector arrows here, but this can be applied in any linear direction. So we also have another constant acceleration equation of motion. The final velocity, here's 1v velocity, equals the initial velocity plus acceleration times time. So the velocity is linear in acceleration as we would expect in constant acceleration situation. We also have the change in position is equal to the average velocity times the time. And we have another of these constant acceleration equations relating the position as a function of time to the derivatives of position. So this is actually Maclaurin series, as some of you guys might know from calculus, that has the final position is initial position plus the v at the initial time times the time interval plus 1/2 a times the time interval squared. And we can manipulate these equations to give us this kinematic equation, v squared equals v naught squared plus 2a delta x. So we will try to understand this machine, knowing this about mechanics. So first off, we notice that the machine sitting on its own is pretty boring. It's in what we call mechanical equilibrium. In fact, if we do like this and change the relative position in the vertical or y direction, we see that aside from some jiggling in the wind, this system isn't too exciting. So in this condition, we see that the system satisfies mechanical equilibrium. And this amounts to having the sum of the forces on each of these masses, say. So the sum of the forces on one equals m1 a1 equals 0. And if we can draw a free body diagram for one, we know that the force is the force of tension in this direction, and the other force acting on it is its weight, m1g, and this is tension for one. We can do a similar trick for the second mass, and we have in equilibrium, 0 is equal to ma2 equals to T2 minus M2G. And we also are not done here for establishing equilibrium. There's a condition that relates to the tendency to rotate, and this isn't rotating here. So the sum of the moments, which are forces applied about a pivot, and it's each moment is the force times the perpendicular distance to the force, or the moment arm. So all of these are 0 because this isn't rotating. So we have the sum of the torques on the cylinder, which also equals the moment of inertia times the angular acceleration, equals 0. And we also can decompose these torques by the tension that's acting on this cylinder downward. So we call that T1, and T1 would tend to make this thing rotate counterclockwise, so we put a minus sign on it. So T1 times R, where R is the radius of the cylinder, plus T2R, the moment causing this thing to tend to rotate this way. And we have, solving this, the equilibrium condition gives us T1 equals T2 equals, identically, T. And we might want something more interesting than this. So if we put a mass on M1, we notice that the Atwood machine immediately gets out of equilibrium. So we can write the equations of motion for that one. So let's have this now be non-zero. So let's have M1, A1 equals T1 minus M1G. But we still have the tensions being equal because we have a negligible moment of inertia for this. We are idealizing this as a frictionless pulley system. So let's drop this subscript here. And we also have M2A2 equals T minus M2G. But we notice that the acceleration going here is opposite the acceleration going here. So A1 equals minus A2. And let's call this identically A. So let's call A1 identically A. So now we have a situation where we can solve for the ratio of the acceleration of these weights relative to the gravitational constant, G. And we get M2 minus M1 over the sum of the masses, M1 plus M2. And I invite you to apply this to cases where you could measure the time it takes for this apparatus to exhaust its entire length. So we can do some empirical tests noting with this kinematic equation of motion, we have delta y equals v naught y delta t, well, we started from rest, so this is 0, plus 1/2 ay delta t squared. So using this, we can estimate what the time that this would require under the assumptions that we have. And we should get that delta t in this set of relations is going to give us delta t equals the square root of 2 delta y over a, where a is solved here. Thank you.